All right, let's talk about intermolecular forces and how these things affect the bulk properties of materials. And when I say bulk properties, we're talking how does it affect things like what phase it's going to be in. This means like is it going to be solid, liquid, or gas? Or how does it affect like boiling point, whether or not it dissolves in water, its freezing point, things like that. So if we're going to talk about the forces acting between particles, we have to consider a couple of things. When I'm talking about particles, I mean the individual atoms or molecules in a substance and how they interact with each other. When we talk about individual atoms or molecules, we're saying that these molecules, they have two competing forces. On one hand, there is energy. The fact that they have a temperature greater than absolute zero means that they're vibrating, and they're vibrating away from each other. So energy, i.e. having a temperature, is enough to make the particles vibrate randomly, and that vibration tends to pull them apart. But on the other hand, there's this intermolecular forces, which is the fact that the particles also pull together. So energy, as in the fact that they have a temperature, is causing them to vibrate apart. But on the other hand, they're also pulling toward each other with these intermolecular forces. And the way these balance out determine what the state is. If the intermolecular forces are stronger, then the forces pulling together are stronger, and you get a liquid or a solid. If these are weaker than the kinetic energy forces pulling the particles apart, then you get the particles separating, and that makes a gas. So one of the things we need to look at is the strength of these intermolecular forces of attraction. Intermolecular forces refers to how much the particles pull each other together. So an example being like magnets would be a good way to explain this sort of a thing. And I have some magnets here, both strong and weak magnets, and I can separate them out from each other to help kind of make the point of what the difference is between strong intermolecular forces and weak intermolecular forces. And to help make that point, I'm going to split these magnets apart so that I put all the strong magnets together to simulate strong intermolecular forces. And the weak magnets will simulate weak intermolecular forces. So let's see, there's another magnet, and here's another magnet, and there's a weak magnet right there. And I can separate this last one, and that's going to allow me to have strong magnets and, oops, there we go, weak magnets. So strong intermolecular forces refers to situations when particles, be it molecules or individual atoms, pull together strongly. If they pull together strongly, they're more likely to make a solid or a liquid at room temperature because, like a strong magnet, if they pull together really strongly, it's hard to separate them. Like these magnets that are really hard to separate. So if they're hard to separate, well, they don't want to separate. Likewise, the particles, if they don't want to separate, stay together. So separation is like turning into a gas. As after all, solids, all the particles are together. Separation is when they vaporize. Strong intermolecular forces mean particles stick together and don't want to vaporize. On the other hand, weak intermolecular forces make it easy to separate. So these magnets are very weak, so they're easy to separate. Likewise, weak intermolecular forces mean that the particles separate easily, which means they vaporize easily. So strong intermolecular forces, the particles stick together and don't want to separate, so they don't want to vaporize. Weak intermolecular forces, like a weak magnet, they don't stick together very strongly, so they're easier to separate, which means they vaporize more easily. So I'll move those out of the way. So that's why weak intermolecular forces is more likely to make a gas because they separate easily. Strong intermolecular forces are more likely to make a solid or a liquid because they do not separate easily. So at room temperature, they're more likely to be still together and making a solid or liquid. So another thing to consider, if it's a solid at room temperature, that means you have to increase the amount of energy each particle has in order to get them apart. So just like when it comes to these strong magnets, I have to pull harder to get them apart. With solids, you have to increase the temperature so that the particles vibrate more, and eventually they'll vibrate so much that they'll just come apart. If you increase the vibrations on these particles, eventually it'll be enough to pull them apart, and that's what melting is and vaporization is. Like iron is an example of strong intermolecular forces. You can turn it into a gas, but you got to get it really, really, really hot because you got to put lots of energy in. compared to something with weak intermolecular forces, where already at room temperature, the energy is enough to pull them apart. So you got to get them very cold before they turn solid. Example is nitrogen. You have to get nitrogen very cold before it goes from a gas down to being together, because you have to reduce this energy to the point where the very weak intermolecular forces can pull them together. And that's what makes nitrogen have to be very cold in order to be a gas, because you have to reduce the kinetic energy so that the weak intermolecular forces become able to pull the particles together to make a liquid or a solid. All right, now let's look at some other things. So intermolecular forces make a lot of difference in whether something's a solid or a liquid at room temperature, or whether it vaporizes a lot or just a little bit, or whether it even dissolves in water or not. We have to understand this is not a chemical bond. Intramolecular bonds is when is inside an atom. Intra means inside. So this is when atoms stick together to make a chemical bond. Those are very, very strong. Intermolecular forces are when entire molecules attract to each other. So that's the example here. A covalent bond is intramolecular force. The attraction between two of these molecules is intermolecular force. So this determines a lot of the properties of these substances. Now, to look at more concrete examples, we need to look at the types of intermolecular forces that there are. Let me get this whole thing up. So the types of intermolecular forces, why do we care about this? Because by comparing the different types of intermolecular forces, we can compare different substances and make predictions about which one's got a higher boiling point or a lower boiling point or more volatility or less volatility, etc. So dipole-dipole interactions have to do with the fact that dipoles exist in covalent bonds that are polar covalent bonds. So a polar covalent bond is when you have atom A bound to atom B, and if atom A attracts more electrons, it'll have more electrons on its side, and since electrons are negative, it'll have a partial negative on one side, and if you got partial negative on one side, it's because you pulled negative charge away from here, which leaves a positive charge as what's left behind. So if you got two of these, and the partial negative and the partial positive, they will attract each other. So dipole-dipole interaction just is saying that a polar covalent bond will attract to another molecule that has a polar covalent bond. Dipoles only exist in a polar covalent bond. Ions don't make this. Non-polar covalent doesn't make this. Noble gases don't have this. This is only found in polar covalent bonds. And I should say molecules that contain polar covalent bonds. So what that means is, if molecule A has this, or some molecule has this, and you compare it to another molecule that doesn't, the molecule that has this will have stronger attraction, which means it doesn't separate as easily, which means it can't evaporate as easily, which means low vapor pressure, or this would give something a lower vapor pressure compared to something that doesn't have it. This would give something a higher melting point compared to something that doesn't have it. And this would give something lower vapor pressure, it would evaporate less, it would have less volatility compared to something that doesn't have this. So when it comes to these dipole-dipole interactions, that's what is being shown on here. And I know the text is very small, but what it's showing is this molecule is polar and has dipole-dipole interactions as a result. So because it's polar, its boiling point is negative 23 degrees Celsius. Because this one is not polar, it does not have dipoles, which means it has no partial charges, which means there's no charges for these molecules to use to attract each other. So they don't stick together as much, they evaporate more easily, and that's why it has a lower boiling point. It's because the particles don't stick together as much. This is true for all the rest of these two, polar and nonpolar. Therefore, this one has a higher boiling point, 97 versus 59. Polar versus nonpolar. Therefore, the polar one has a higher boiling point, negative 21 versus negative 89, because these ones are able to pull each other together and make it so they don't evaporate as much and they can't separate as much. These are unable to pull each other together. Therefore, they have a lower boiling temperature. Okay, because after all, if they pull each other together, then they don't separate as easily, which means you have to put more energy into forcing them to separate, which means you have to raise the temperature to force them to separate, which means a higher boiling temperature. All right, now let's see, what's the next thing we can look at here? Hydrogen bonding, this is a key idea, an especially strong form of dipole-dipole interaction. It's not its own thing, it's just a form of this. So, okay, dipole-dipole interaction makes particles stay together more, which makes them evaporate less because they can't separate as easily, which means you have to raise them to higher temperatures in order to make them evaporate more, which means they have a higher boiling point. If you have this, then it raises the boiling point even more. It results when your dipoles, which is to say your molecules that have a covalent bond, contain particular elements. It gives this list right here. So when these elements are there, it makes it possible, and no, we're not going to ask people to memorize that. What needs to be understood is that if it's especially strong, you should predict that it's going to raise the boiling point, it's going to raise the melting point, it's going to reduce the amount that it evaporates, which means lower vapor pressure, lower volatility. So in terms of what we need to get out of this, you should be able to predict about those properties, the higher vapor pressure, the higher boiling point, the lower vapor pressure, like that kind of a thing. And I know I haven't mentioned these things like vapor pressure before or volatility before, that's from notes 15, but for those of you who have already completed the unit and are looking back at this for review, it's meant to help you with that. All right, now let's see. Ion forces, note that these are the strongest type of intermolecular force. And because stronger intermolecular force means sticking together even more, that means even higher boiling point and even lower tendency to evaporate. So that's why it gives like a really, really high boiling temperature. Ion dipole forces are not as strong as ion-ion, but it's stronger than dipole-dipole, because here's the thing. Dipole-dipole is kind of strong because it's attraction between two partial charges. Ion-ion is the strongest because it's attraction between two full charges. This is in between. This is stronger than dipole-dipole because it's partial charge attracted to full charge. But it's not as strong as ion-ion because ion-ion is attraction between two full charges, and that's not what this is here. London dispersion forces are the weakest of the intermolecular forces, which means they're going to produce molecules that are most easily able to separate out of all these forces. Which means anything that has this London dispersion force as its only way of attracting other molecules is going to have the greater ability to separate, which means it separates more easily. That means it evaporates more easily. And if it evaporates more easily, that makes lower boiling point because less energy is needed to make it boil. It has more volatility. It has more tendency to vapor pressure because it has a greater tendency to evaporate, all due to those very weak intermolecular forces. Now, this is a description of what happens. It's that the electrons are moving around randomly, and because the electrons in different atoms are moving around randomly, every once in a while, just by chance, they'll happen to pile up very temporarily on one side. And when they do, it makes the other atom stick to it, because it'll push the electrons in the other atom away, and then they'll start sticking temporarily, and then it'll soon end, and they'll drift back apart. So it's weak. It's nowhere near as strong as the other types of intermolecular force. That being said, in one atom, it's very, very weak. In multiple atoms, it can add to a very strong force, which is why a small atom that only has this force will have a very low boiling point. Kelvin is this is like negative something degrees Celsius, it's like negative a lot. On the other hand, a very large atom with lots of electrons will see a much higher boiling point because although London dispersion forces are extremely weak, in large atoms and especially in large molecules, they can add up to be very strong. It's like a penny is very little money, but if someone has 1,000 But if you put together like 1,000 people that each carry 1 penny, that can add up to a lot of money. Likewise, each individual atom, this is very weak, but if you have a molecule with many atoms, each atom contributing its teeny little bit of London dispersion force, it can add up to quite a large amount of force. So large molecules, if this is all they have, if the molecule is large, it can have a high boiling point and a strong intermolecular forces. And let's see, wait, what is this? Oh, this is an animation of London dispersion forces, where the electrons move to one side on one atom, and it forces the other atom to have its also the electrons move to one side and make a charge, and then they stick together temporarily. It's a temporary thing. So summarizing the intermolecular forces, yeah, we talked about 5 different ones, and you, the viewer, what you need to be able to do is organize them from strongest to weakest, which I've done that for you here. Strongest, second weakest, weakest ones, and then, sorry, actually I should point out, there we go, strongest, second strongest, this is not as strong as this, but it's still stronger than this, and then this is not as strong as this. Okay, sorry, I pointed the wrong thing. This, what I should have pointed to here, these are the types of bonds that produce these forces. So ion-ion interactions only happen in stuff that has ionic bonds. Polar covalent bonds is going to produce hydrogen bonding and dipole-dipole interactions, depending on which kind of things are in that polar covalent bond. If it has hydrogen or oxygen or nitrogen, it might produce this. If not, it'll produce this. Non-polar covalent bonds produce only this. If it has no bonds at all, it can also produce only this. So by looking at the type of bond in a molecule, you should be able to predict what kind of forces are being made, and you should be able to rank the forces from strongest to weakest, and these are just 3 of the same thing, so from strongest to weakest. And then based on that, predict things like highest boiling point, lowest boiling point, highest vaporization, most tendency to separate and evaporate, least tendency to separate and evaporate. And then you can make predictions based on that. Now, having said that, we need to talk about one other thing that this affects, which is the tendency for something to be able to or not able to dissolve in water. And this goes back to knowing what kind of interactions are going on in terms of ionic or dipole or things like that. So solubility is the ability of something to dissolve. Like dissolves like. So when it comes to solubility, we're saying that if something can dissolve in something, it is soluble. For example, sugar dissolves in water, therefore sugar is soluble in water. Sand does not dissolve in water, therefore sand is insoluble or is not soluble in water. So polar covalent compounds, if they are polar covalent, then they have the dipole. So here's a polar covalent compound with partial positive and partial negative charges, maybe A and B, whatever. Water is a polar compound. It has a partial positive on this end, the hydrogen end, and a partial negative here. So it can attract to anything that has a charge. Ions have charge, therefore ions can interact with water and will dissolve in it. Polar stuff, maybe like this hypothetical molecule, also has a charge and can interact with water. Non-polar stuff is maybe element C and element D. They are sharing their electrons evenly, which means there's no partial positives and negatives, there's no partial charge at all. So there's no delta anything, there's no partial charge for this to attract to, so this is not attracted. And because it's not attracted, they won't hang out together, which means they won't mix together, they'll stay separate. We all know oil doesn't mix with water, and that's why. The oil molecules are not attracted to the water molecules because they don't have any charges. The waters are not attracted to the water, or the waters are not attracted to the oil because the oil doesn't have any charges. So the water will be unable to mix with the oil, and that's why there's no partial charges on the oil because it's nonpolar. So nonpolar means no partial charges, unable to mix with stuff that has polar or ionic bonds. So that's why, likewise, what do you use to dissolve something nonpolar? The answer is something else that's nonpolar. Those are the only things that can mix. Otherwise, they'll separate themselves away from each other. If you have something that's charged and something that isn't charged, they'll separate. If you have two things that have a charge of some kind, they'll mix. If you have two things that don't have a charge, they'll mix. And that's what happens. This example, PCE is used for dry cleaning. That is something that is able to be done, or that's something that's able to be done because this chemical can mix with this chemical because they're both nonpolar. So, having mentioned that, the next thing is this thing with having to do with how soap works. So for soap, we said polar only mixes with other polar stuff, nonpolar only mixes with other nonpolar stuff. Soap's superpower is that the molecule has a nonpolar portion that can mix with nonpolar things such as oil, and a polar portion that can mix with polar things such as water. Since the molecule has those two parts, it can mix with both at the same time, and so that's exactly what happens. The molecule that has its nonpolar parts mixed with grease or oil or whatever else is nonpolar, the polar parts mixed with water, and then it kind of makes them into the shape and carries them away because it's able to interact with both, it can allow them to mix together. And that's why soap can get maybe oil or grease off your hands. It's because it's got those pieces to be able to interact with the polar water and the nonpolar oil or grease. See, all right, I think that should cover it.